sir.
Thanks, Thomas, for the introduction. Well, the crowd has probably reduced a little bit, but that's okay. Many of you may be wondering, why quantum computing in a security conference? I'll talk about it, but I hope it will rejiggle some of your minds, give you a little bit better perspective of a new field altogether. For me, coming out of this conference, I'm a security guy by profession, though, but talking about quantum computing, this is my past research, my passion to this date. So we'll talk about why this presentation in a security conference, or maybe to tickle your brains to understand where are we going into the future. I guess it's all about the future. You know, we learn from past, we go into the future, right? So I'll try my best. It's more of, the presentation style is more of, you know, picture says 1,000 words. So less of a content, more of a picture and a philosophy behind it. By the way, Prashant, again, I work in Alberta Health Services, an IT security architect, 10 plus years of experience in security. I have a master's and bachelor's back from India, and I have done a couple of years of research in this field of quantum computing. If you Google my name, you will find around 4 research papers, one of which is in MIT Boston, quite a long time back. I've forgotten all the mathematics, so don't ask me questions if there's any mathematics involved. I mean, this is pretty much just tickling your minds as to what this field is all about. I go by the name of Guy Farkas, so that's my handle on Slack, on the YXSec channel we have here in Edmonton. I've made a little bit of a change in the subject. So this is quantum computing, a new paradigm, rather than quantum computing with some security ramifications. Because, you know, I thought about it a little bit. Yes, security is important in this field, and I'll talk about it, but I think this is more general. I got to give you an introduction why this field is what it is, rather than talking the details on what security is all about. So why quantum computing presso? Harvinder came to me when they were starting this B-Sides conference. They said, you know, would you like to speak on a topic? I've done some security engagements before, but I said, yeah, maybe I can talk about quantum computing. Why not? I mean, that's part of my research. But what tickled my brains was this motto of the B-Sides, you know, in general, as this was being discussed in the morning, right? This is the goal of B-Sides in general. It's a community-driven exercise. It's a, you know, it's a forum. The goal is to expand your spectrum of conversation beyond the traditional confines of space and time. That's quite close to my heart. Space and time, when it comes, you know, it talks physics. I love physics. Quantum computing is marrying physics with computer science. I'm going to talk about it. So I don't know how many of you have, I'm sure everybody has learned physics in some time in their life, but physics in general seems to be, you know, it's some philosophy or it's a thing out there. There are scientists who are doing it in the background. What's it in for me? Or what is it? What the practical implications of it are? And marry computer science to it, and this is a deadly field of quantum computing which comes up. Actually, U of A, folks who are from U of A would know there is actually a world-famous nanotechnology research lab out here in Edmonton. Now, I'll give a little bit of a difference. What is nanotechnology? What is quantum computing? There's a slight difference, but they ultimately come down to that level where normally you and me, the way we understand life and science, doesn't work. There was a very big scientist. We were actually having a chat in the lunchtime with some of my folks, a great scientist in this field of quantum mechanics, and he said, if you're not confused by quantum mechanics, you have not understood it. So my goal here is to confuse you guys and hopefully make it a little bit more muddied water as to what this field is about and see how it goes. The other thing I liked of this motto was it is where conversations for the next big things are happening. So we are in Edmonton, you know, Edmonton Go, B-Sides conference. Why not talk about a field which is still in its nascent phase? There are some practical applications of it, so I'll talk about that as well. Let's do a little bit of a philosophical ride in physics. For those who are interested in it, I'm quite interested in, you know, how physics tries to explain the world. So I don't know how many of you can understand who this guy is from his hairs? Albert Einstein. Right? The probability of them visiting unexpectedly is directly proportional to how much you feel like being left alone. Actually, I got my wife and kids to the airport today. They have gone home, so I'm alone. And hopefully this statement doesn't come true that they come back. They'll be coming back in a month's time. Because we are living in classical physics. I'll talk about the Newtonian mechanics, not in quantum world, where things can happen right off the bat and you don't expect it. So starting at a humor, Einstein was actually one of the person who didn't like quantum mechanics, and he had a big debate with this other guy, Niels Bohr. Niels Bohr, he's called the father of quantum mechanics. Einstein is called the father of relativity, if anybody has heard that term before. Special relativity or general theory of relativity. The way gravity works, the way space-time is curved. Can you even imagine, at this moment, I'm looking at your past. I'm not looking at your present. Think it for a moment. This light has gone to you, and it has traveled from you to me. There is certain time back when I'm looking at you. Things change, philosophies change, and that's where Einstein said, general theory, I believe in a true cause and a true effect. Niels Bohr said, no, maybe that's not true. So, basically Einstein said, God does not play dice with the universe. There is no uncertainty in this world. Things need to be certain. While Niels Bohr said, no, that doesn't make sense. Quantum mechanics is important, and it's a field, and there are things which are uncertain until you measure them. So I'll talk about that a little bit. It's a very subtle philosophy, but the moment you understand it, it kind of rejigs your brain and gets you involved. Why are we in this world the way we are? The fact that I'm looking at your past, I'm looking at these stars out there in the morning or in the nighttime. I'm actually looking at how many billions of light years back in time, as you may have Googled and you have seen, right? They may not even exist at this point of time from where the light has traveled. And light is the fastest the speed of light is the fastest in this universe, as we all know. That's again Einstein's postulate of his general theory of relativity. So God does not play dice with the universe. Actually, Niels Bohr replied back to this, and he said, not only God plays dice with the universe, but he throws it in areas where you cannot even see them. One another interesting quote, as Einstein always used to say, great spirits have often encountered violent opposition from mediocre minds. So he actually called Niels Bohr as a mediocre mind. Can you imagine? That's how the rivalry between scientists happen of two different thoughts, two different schools of thought in science. And none is right or wrong. They have different perspectives. And I'll come to that. But they have very interesting perspectives of how to look at the world. One another interesting quote which always keeps my attention, reality is what is observed. Reality is what it is. Think it for a moment. You have a tree out in a forest. It is existing out there. You haven't seen it. It still exists. Niels Bohr says, no, it doesn't make any reality for you because you haven't gone and observed it that it is standing in out there. I'm looking at you. You are a reality for me. If you're not there, I mean, it defies classical thought. Yes, people exist. They don't exist because I cannot see them. But in the world of atoms and molecules and particles, this actually becomes true. And that's why Niels Bohr succeeded in his theory of quantum mechanics. I'll give a little bit of what it is, then we'll come down to computer science and why quantum computing is taking off its roots. Okay? Very interesting. I mean, at the end of the day, when physics takes over, we know physics, chemistry, biology. At a certain point in time, when you keep thinking about it, you move into the world of metaphysics. Then you move into the world of philosophy. Then you probably move into the world of, the Maslow's triangle, if everybody knows, the Maslow's triangle of self-actualization. I mean, why am I really there in this world? What's my purpose? What am I observing? Is this all reality or unreal? Am I going to die someday, and what's going to happen to me? Right? Another interesting one. I want to know God's thoughts. Rest are details. So he was a great philosopher. And you all know E equals to mc squared. one of the greatest equations ever found by him, is why it's quite interesting. You know, I was thinking about it when people were giving a presentation. I mean, this is a pen, right? This pen has a mass. If anybody knows physics, a mass, like it's a material, right? This material can be changed into energy. It can be absent at this point in time, and it all becomes energy. That's exactly how nuclear bombs work. That's exactly how atomic bombs work. The theory of nuclear fission or nuclear fission, you know, if you want to Google around why hydrogen bomb is what it is, why an atomic bomb is what it is, you're basically changing matter into energy. The fact that that even exists, the fact that energy and matter are interchangeable is fundamental. And that's what he said, right? So he wanted to know why God's thoughts, you know, what exactly is the reality, and he wasn't concerned how to project or how to understand that reality. And that's exactly what quantum mechanics does. It's a theory. It's a model. It may not necessarily mean that it's reality in itself, but it can give you answers of the reality or things you look at correctly. And that's why it's successful to this date. So there's we all talk about modeling theory. There's a model, then there is reality. How you model that reality and how you can find true answers of that model, of that reality, for example, then that model is correct. Special theory of relativity, quantum mechanics, any theory you talk about, okay? Particle physics. So back from quantum mechanics into particle physics, right? Everything is made of atoms and molecules. You go a step further down, neutrons, protons, and electrons. You go one step further down, quarks and leptons. You go one step further down. They call it the God particle. I don't know why they call it the God particle. It's called neutrino. And in the CERN lab out in Europe, they actually have an underground lab where they collide different particles together. They claim to say that they found the fundamental particle which can explain everything, but there's a debate around it. My point is this, if you look from the scale of a nucleus, or even, we'll talk about quarks and leptons, to a scale of an atom, to a human being, down to the scale of a universe, to the scale of galaxies, do you see like there is a pattern emerging out of it? That pattern is what is in the microscopic scale can be on the macroscopic scale, and they are actually mimicking each other. Newton was actually one day sitting on his desk, and somebody came, and he was making a model of the solar system. Somebody said, wow, what a beautiful and a perfect model of the solar system. I'm a theist. I believe in God, so I'll speak in that terminology. I'll try to argue why there is a superpower. So he said, so Newton was there, and he said, okay, what a beautiful model of the solar system. He said, yeah, this is what I made. Think about the solar system existing out there. Somebody might have made it to the fact that electron, if you know electron, it's a negative particle, right? It's a negative charge. 10 to the raise of minus 19 coulomb is its electrical charge. Even if you change 10 to the minus 20 or minus 18, I mean, you could imagine, do the zeros, this universe wouldn't exist. The way you and me are here will not exist, just because of the fact that you have changed a slight decimal in the charge of an electron. That's how precise this machinery of the universe is working. When Newton said, I could make this and you like this so beautiful, think about the solar system of the universe. Somebody might have made it, or how perfect and how precise it's going. So particles, right? Matter is made of particles. You have matter, you have atoms, electrons, nucleus, then neutrons, and quarks. The more deeper down you go, the more you find. But what I imagine, I'm not a particle theorist, particle physics physicist, but at certain point in time, the particle nature of matter will cease to exist, and you will only have waves or energy in this vacuum. And that's what E equal to mc squared is all about. I'll just give you an example of what an atom might look like. It's just a model. And this model speaks volumes, actually. if you look carefully of what we are looking at here, we are looking at the center of this atom, which is the nucleus. We're looking at a cloud. We are not actually looking at the way you always imagine an atom as electrons and protons going around it. This is what quantum mechanics is. You have a probability of that electron somewhere in that location of space, but where it is, you don't know, because our precision, our understanding breaks. This is where, if you have heard Isaac Newton, right? The apple fell, he said, oh, how come gravity doesn't exist? Or what this force is which goes down and why not up? And then he came up with these 3 laws of physics, right? Newton's first law, second law, and third law. It went along for 200 years until Niels Bohr came, or the quantum mechanical world came, to a point where this classical thought that action and reaction, force equals mass into acceleration, or that inertia, a body does not move until somebody pats it or forces it to move. That thought breaks down. You come into the world where it is all haziness, where there is probability of things existing, but things existing of themselves is not a reality or precise in nature. So this is just an example of how you can visualize an atom from a quantum mechanical perspective. This would be important because I'll be talking about quantum computing, so why this probability is important. Hope I'm making sense here and it's not going over the board. I'm just trying to bring it down to a point where it tickles minds and again gives you guys idea. Maybe you can go a little bit more Google queries on what quantum computing is. So Moore's law, how many of you know what Moore's law is? Okay, why is it called a law? It's actually not a law. It's an empirical observation. A law is always precise and perfect. Gordon Moore, who was IBM's chairman in 1965, around 1960s, he observed that the density of transistors on a microchip or on a controller doubles every 2 years. It's precisely 18 months, actually, but every 2 years. If you extrapolate this law in time, what you will see that the number of transistors will keep on doubling on a microchip or a processor or controller. And how could they double on the same space or in the same area? They have to keep getting shortened and shortened, right? They have to keep going smaller and smaller to a point where it will come that a transistor would have its dimensions in the range of an atom. And when that happens, you're not in the world of classical physics or Newtonian mechanics. Those zeros and ones don't matter anymore. I'm sure everybody know a 1 is a 5 volt on an electrical wire on a motherboard, right? Like it's a signal, and a 0 is a 0 volt, right? This certainty of either you have a 1 or a 0 breaks in that world of quantum mechanics, as we have been telling, that probability exists. So Moore's law is going to break someday. I mean, at some point in time, the transistors will be a point of an atom, and then different physics altogether takes over. And that physics will then drive quantum computing, which we'll talk about, qubits and whatnot. Makes sense? Like you are at a point, and we are actually at that stage. We have not realized it yet, but the stage where you're moving closer to nanometers, micrometers, nanometers, and even further down to the level of, so talk to Intel, talk to AMDs of the world, they will tell you how small the transistors are. And these are the building blocks of a computer, right? A transistor is a 0 or 1, right? You actually look at how the bits get arranged in there. So what is quantum mechanics? I mean, I've been talking about it for a while now, but just a quick overview. It is a framework for the development of physical theory. So it's a framework, okay? It's a model of reality, not reality in itself. It is not a complete physical theory in its own right. So it has its limitation that it works in the field of atoms and molecules. Then at a certain point, Newtonian mechanics takes over, which is Isaac Newton's way of looking at things. Those 3 laws I talked about, right? Inertia, action and reaction, force equals mass into acceleration. Now, where can quantum mechanics come into play and drive computing? This is the beauty of marrying physics with computer science now. Information theory with how computers can get changed. They have to, right? If the Moore's law has to break, your hardware has to change or things would have to be different. So application software, operating systems, standard stuff, right? That will always remain for an end user to understand what they're looking at. I mean, those things would remain. Certain specific rules of algorithms, of generating, processing power, of running the show at the back end, when your density is so strong that there's no Moore law anymore, would be run by quantum mechanical rules. Atoms and molecules, qubits, things talking in probabilities. So quantum mechanics has 4 mathematical postulates which lay a ground rules for our description of the world, and I'll talk about it. Basically, there's those 4 fundamental principles. If you understand them, you can understand how this field can run computing sciences. And they're quite interesting and very, counterintuitive. As I said, if you are not confused by this field, you have not understood it, as Niels Bohr said before. How successful is this field? Unbelievably successful. This is a mathematical model of the world, but think about it, like those brains in 1930s and 40s created those postulates. They have been running. Actually, quantum mechanics, I don't know how many of you know, in the world of physics, they're talking about theory of everything. I'm not sure that's true. Again, I'm a theist, so I understand human beings may not understand theory of everything because we are part of the same equation. How can we understand ourselves by our own selves? So it's a little bit of an oxymoron. But they say a theory of everything would also need to have quantum mechanics as a component of it. You cannot have atoms and electrons, you cannot explain them until quantum mechanics is part of it. But quantum mechanics has not explained everything of this world. Think about gravity, right? I mean, I had this, again, right? You throw it, it comes down, right? This simple fact of something going up and coming down, which we all know, as Newton said, why apple is coming down, not going up. This gravity cannot be explained by quantum mechanics. And this is a problem for scientists these days. They can understand a lot of things, but they cannot understand gravity. So theory of everything would include something more than what quantum mechanics tells us. Okay? So, they're talking about gravitons. They're talking about tachyons. I mean, it's a very fascinating world. If you know light, as we all see here, there's photons going back and forth. If you heard that term, particle of light is called a photon. They're telling a particle of gravity is called a graviton. Why gravity is just a force? It could be a field with particles. It could be understood in the nature of particle physics the way light can be understood in the nature of photons. Talk about tachyons. It's a conceptual concept, but they said tachyons are particles which can run faster than the speed of light. And if that happens, I don't know how many of you have heard special relativity. If you run faster than the speed of light, you can actually go back in time. And there's a grandfather's paradox. If I can run back in time, I kill my grandfather, then my father wouldn't be born, then I wouldn't be born, but I'm here. So how is that possible? So there's a theory behind it, but to this date, the postulate that light is moving is the fastest speed in this universe still stands. So quantum mechanics, we talked about it at length. How does information theory or computer science comes into play? So let's go bottom up. So information theory, you have different different fields around it, right? You have statistical mechanics, cryptography, computer science, the Turing machines, if you have been into computer science as a graduate, Turing machines and what they actually mean, Shannon's theorem of information theory, error correction, etc. This is standard computer science 101. You keep going up, then you come into the realm of quantum algorithms, quantum computer, error correction in the world of quantum mechanics. And then you keep going up, and you actually are marrying the field of information theory or computer science with what you can actually do with quantum mechanics. At the end of the day, quantum mechanics is only providing you the resources to do computation. That's all. Just like bits, it's electrical wire, zeros and ones, right? Electrons up and down. In a similar fashion, quantum mechanics is providing you the resources. You could use those resources create your own quantum algorithms, and then go after it. There are famous algorithms in quantum computing to this day. Shor's algorithm. You can actually break the RSA algorithm if you have heard RSA cryptography, right? We talk about keys, 1024 or 128 to 56-bit RSA cryptography. These can be broken in the world of quantum computing. And I'll tell you, actually, IBM created a 7-qubit quantum computer, coding qubits on top of molecules, and they factored 15 into 5 and 3 back. So these are prime numbers. Those who understand cryptography, right? Prime numbers, you can go one way easy. It's hard to refactor it back into prime. They did that. The fact that it is 15 back into 5 and 3 is probably not that important, but the fact that you could do that is important, because now you can break RSA algorithm with this computational method. So what is quantum informatics? The basis of information theory is discrete mathematics, binary digits, as we all know, zeros and ones, right? Quantum information employs quantum states as basic elements of information. So we'll talk about those, what the states mean, but in a term, it's probability. Examples of quantum bits or qubits are like nuclear spin. It could be motion of a trapped ions. It could be photons in an optical resonator. Each offers a future technology for future computing processing. These are your resources. These things you can use to code information in the form of qubits, and then do your mathematical algorithms on that, get the results out, and lo and behold, you are breaking a lot of stuff which currently exists, or you're creating new stuff which does not exist even today. So again, the same thing in a pictorial fashion, but I'll show you a little bit of a video again of what a qubit might look like. This is an example of a photon going up and down, up and down, up and down. Just an example of a particle of light. I don't know if a light can be measured in wave or in particle. This is a very famous principle, but not both at the same time. Either you are a matter or you are a wave, but you cannot be both. Does that make sense? I mean, it's a little counterintuitive, but either I'm a person or I'm invisible, but I cannot be both at the same time, right? So, so this is an example of how a qubit would look like. A qubit is not an electrical signal. It's a resource provided in the world of quantum mechanics. Again, ions, photons, atoms, electrons, and they can be coded into these qubits. Again, zeros and ones. The beautiful fact here is, and I'll talk about it, it's called the principle of superposition. You can actually have 0 and 1 at the same time coded on that resource of a qubit. It's not either or. It's both. And when you look at it, we'll talk about it's a problem of measurement, then only one. I mean, if I'm looking at you, you are there. If I'm not looking at you, you may or may not be there. That's what Niels Bohr said, right? So, but the moment I look at you, you are there. So you are a fact for me. Some of the benefits which quantum computing can provide. So quantum information is inaccessible until converted into real information via measurements. A very important fact, and I'll come to that. There'll be actually a topic on Schrodinger's cat paradox. If anybody remembers their physics again, in quantum mechanics, there was a cat paradox. And it offers security in quantum cryptography and other sharing protocols guaranteed by laws of physics rather than assumptions of mathematical difficulty. A very fundamental statement here. Security is never 100%, as we all know, right? I mean, we could pay a lot of money to try to secure ourselves or be, lock ourselves and try to be 100% secure, but there are always ways to break it. But that's, or in cryptography, you talk about mathematical difficulty algorithms and you try to break them and you cannot because the supercomputers can't do that today, and so it's not possible. But in quantum cryptography, where actually I did my research back in Montreal, my professor was Dr. Gilles Prashant, who is the father of quantum cryptography. He created a protocol called BB84, Bannett-Brassard 84 protocol. We'll talk about it. It's a cryptographic protocol. But the fact that if it is secure 100%, because if it is not, then you're falsifying a law of physics. And I'll talk about it. It's called the Heisenberg uncertainty principle. And that's actually a law of physics in quantum mechanics. So either you go against the law, which would be awesome. I mean, if you could break that, you'll be obviously famous tomorrow, because now you're not just famous in security, but you're famous in physics world too. But you cannot break that law, and that's why you can ensure that the security of this is 100%. And entanglement of states makes some uncomputable problems computable. So we'll talk about entanglement. Spooky action at a distance. Anybody heard that term before? Beam me up, Scotty. Spooky action at a distance. We'll talk about it. I mean, it's so counterintuitive again, but we'll talk about it as the slides come. But this is a fact of reality. It's in fact true, and they have done experiments around it. Schrodinger's cat paradox is Dr. Schrodinger, Erwin Schrodinger, 1930s. Beautiful cat paradox. So there is actually that nuclear material out there. So there's a particle which can either be emitted from that nuclear, call it a resonator or an emitter, for example, or a particle may not be emitted from it. Now, since it is quantum mechanical in nature, because the particle is so small, like it's a nuclear material, there's a probability of 50-50 that it will send it or not send it, right? The qubits, zeros and ones, can be at the same time on a machine. So because it's in a box. You're not seeing it from outside. You don't know what's happening. Keep that in mind. Now, that particle has a 50-50 chance of being emitted or not. That could lead to hitting a hammer. That hammer hits a poisonous bottle. That poison spills out, and the cat is dead or alive. Now, the paradox is, I'm not looking at this box. Okay? Can I tell if the cat is alive or dead? I may not. I cannot. For me, there is a 50-50 chance of cat being alive or dead. It's very hard to wrap your brain around this idea. But this is how this paradox came into being. Now, the moment I take the box out, yeah, either she'll be dead or she'll be alive. For me, she is a reality now. Either it's a 0 or a 1. But until I observed it, it was 0 and 1 at the same time. Does that make sense? And so that is how they claim that quantum computing with qubits can do such a massive scale of processing, even beyond supercomputers. I was talking to somebody today. I'm not sure if it is 128 bits or 1024 qubits, one of that number. But say it's 1024 qubits. So 1024 qubit quantum computer, just 1024 qubits, like 1 meg, can refer every atom in the universe. That's how large that computation is, and at the same time. Because if I'm not observing what's happening inside that computer, all the processing possibilities are there. However, millions are there, 2 raised to 1024. The moment I look at it, yes, I will collapse it into a state where I will see something which is concrete. But the fact that I can run a computer in a black box with certain algorithms on it, with possibilities of 2 raised to 1024 at the same time, as if like I'm referencing every atom in the universe at the same time in that computer. Just 1 meg of a quantum computer can do that. Heisenberg uncertainty principle, another beautiful principle. So look, I'm here, right? I'm standing in front of you. My position is 0, is straight, and I have no motion. I mean, you can exactly tell that what's my position and if I'm moving or not. This is because you and me can see each other. We are part of the Newton's world, right? This is classical physics, standard, those 3 laws as they apply. In the world of quantum mechanics, Dr. Heisenberg said, if your particle is so small that it is at the level of quantum mechanical rules, then you can either look at its position or you can look at its motion, but not both at the same time. That's not possible. And he proved it, and there are many experiments which prove that. And this is the concept of non-orthogonality. I'll talk about it. So the fact that you can have this principle actually ensures that quantum cryptography is 100% secure. because look at, if analyst is sending a qubit to Bob in a quantum cryptographic channel, I'm not looking at that qubit, everything is flowing by. The moment a hacker or third person, call it a man-in-the-middle attack, is looking at it to try to observe or intercept that message, you have broken its quantum mechanical phase, as I said in the Schrodinger's paradox. You have actually broken its state. It's not correct anymore. It may not be good for Alice or Bob, but it's not neither good for me as a hacker. I may have denied that communication, but I cannot intercept it without interfering with it. That's how you will be breaking a law of physics if you're even measuring to try to look at that channel. So that's the beauty of Heisenberg uncertainty principle, ensuring that quantum cryptography will be 100% secure. Einstein-Podolsky-Rosen paradox, another beautiful paradigm, the spooky action at a distance. You can have two particles at two ends of the universe. They will still talk to each other, even though the speed of light will probably connect them after a long period of time, but they can instantaneously talk to each other. That's what Einstein and two of these other folks talked about. I'll give you a small demonstration of this again. It's a video of what a EPR, I'll talk about it a little bit, looks like. Two particles, the way it works again, from a little bit physics, but you have, say, one particle, right? This particle at this point in time is just one. It breaks for some reason. There's an internal force, it breaks. It goes so far away. The initial momentum is zero, right? It was standing still, right? If anybody knows physics, the law of conservation of momentum, law of conservation of energy, and law of conservation of mass. There will always be conserved. It doesn't change. There'll be only one energy in a closed system. There'll be only one mass. You can break it in how many pieces. So is motion, momentum. So a particle breaks, goes into two ends of the universe. Still, the law of momentum will be correct. That means if I take its momentum going there, and it's there, and I plus them together, it'll still be zero, because the initial momentum was zero. It was just standing still when it broke apart. So the final will be 0, too. Now, Einstein said, if I say that particle has a velocity of 50 kilometers per hour going east, I don't even have to look at this particle to say it's going 50 kilometers an hour going west. I instantly got that information because that law has to remain valid even at the ends of the universe. And that's what Einstein said. Niels Bohr said, no. You have, so Einstein said this, and he said, look, this is possible. Now I can look at its position. I can look at this particle's velocity or momentum. And by knowing this particle's momentum, I can infer what this particle's momentum is without even looking at it. Now I have falsified your Heisenberg uncertainty principle because I know this particle's position and momentum both. Does that make sense? I'm not looking at it, I'm looking at the other one, but looking at that, I can infer this. And so Niels Bohr said, no, you're wrong. They still are part of the same quantum mechanical system. You actually have observed it. You have observed it, and that's why you can see that they are correct. So there was some debate. Again, I'm not maybe correct factually as to what it is, but what I'm trying to say is, he said, look, I can do position and momentum by looking at the other guy. This is, and the fact that you can do it at the end of the universe, think about it. Like a particle at the end of the universe, if it even has to make any change on its brother on the other end, what is the best way you can do it? You have to send a speed of light, a signal, right? That'll probably take eons to go to the other end of the universe. But we are not doing that. What we are doing is just inferring that based on the law of physics. This is called spooky action at a distance, and it is valid. They have done experiments, and it actually happens. So this experiment led to what's the concept of entanglement, which is another resource of quantum computing. And they said, well, this is possible. We could do it. So 3 principles: superposition, non-orthogonality, and entanglement, based on 3 fundamental laws of physics: Schrodinger's cat paradox, Heisenberg uncertainty principle, and Einstein's EPR paradox. They are the resources of quantum computing. You can actually use these as resources, code them on qubits, create quantum computers, and run algorithms on it. Beam me up, Scotty. It feels like science fiction. It may not be. They've actually done an experiment by which they have what they call teleported. The term is called quantum teleportation. They actually have teleported a particle from one location to another using the EPR paradox I was just talking about. And I will show you a little demonstration of that in the particle world. Now, what stops something from the particle world to come into the human world? It's probably time. If you can physically demonstrate something happening in the matter, you may have to find ways how you can do it at the human level or at the matter level, at this level. So, teleportation could be a reality tomorrow. It is what they do in the quantum world. Challenges. So, quantum cryptography has been called, has been achieved, but requires further development. So, again, as I said, my professor, Dr. Gilles Brassard, Bandit-Brassard 84 protocol, if you want to Google it, they have achieved that to run cryptography. I'm not sure. This was kind of a speculation, but in the year around 2005, when I was doing my research, they claimed that the Department of Defense in the US and a couple of universities actually had a running quantum cryptographic channel underground where they were sharing information. It's just like, internet came into the world, but it was already there in the DoD world long, long before. And so you never know. They could be far, far ahead in their technology, and we will only look when it comes into fruition. I will talk about some practical implications of quantum computing. They are actually today, and we'll talk about it. Quantum computers are not yet developed to a full extent. There are certain proof of concepts. Identification of computing problems for which quantum computing is an advantage. We need to know which problems are there, like factoring is one problem they have solved. Shor algorithm is another problem. Cryptography is another problem. There are other computational problems which they have solved with quantum computing, at least in theory. You need to put it into practice. And who knows, tomorrow it could be quantum software and maybe quantum IT. I don't know. How would security look like in the world of quantum IT, where everything is fuzzy, where everything is probable, until it becomes reality when you see it? Just an example of the Bandit-Brassard 84 protocol. Alice and Bob, they send a signal over. There's a full length of steps you need to take. You need to measure those particles on the Bobs and to try to decipher what Alice has sent. But the fact, as I was saying, the fact that when you're communicating with it, if a hacker goes inside it, he's going to break the law of physics. He's going to basically break the communication and break that probability of communication into what is real. And that is not actually what was being sent. So that's how they generate these cryptographic protocols. So just an example of it. A breakthrough in quantum computing. Until I ping the NT server, I don't know if it's up and down. So you never know, right? You could have a quantum ping, and you would know, oh, I don't know if my server is up and down until I know where I can ping it. Consider three aspects. So these are the three aspects: quantum cryptography, quantum teleportation, and quantum computing. So an example of quantum cryptography, how they generate two particles in a cryptographic world. You see an electron hitting an atom, creating two of its brothers, and they are now entangled with each other, going at the ends of the universe. So this is what entanglement is. Now, using this entanglement, you actually can create cryptographic channels and create algorithms around it. Quantum teleportation, this is an experiment which was done, which actually proved that a particle can be teleported from one position to another position. You see there is an emitter of light, so you will see a light coming out from there. It'll go split into two, so we'll let the video run. Those are two entangled pairs, right, as we have been talking about. One of them goes to the ends of its measurement. There's actually four entangled pairs which are there, so it's a little bit more complicated than a two-qubit system. So two of them will match here of the pairs, and they will be measured at this point. And by this measurement, I could tell, as part of the EPR paradox, what that other particle is doing. And I could actually relay that this particle is coming at this position at this time. And what would be its position? What would be its momentum? So, just a pictorial representation, not going into too deep, but they have done experiments to prove this theory. Quantum computation. So, coming back to computer science, what is quantum computing doing in terms of creating practical applications? So, we'll talk about this, but this picture here is of D-Wave Systems in Vancouver, Burnaby. They are a company in the market, and this is the quantum computer they have existing in their lab. You can actually do certain computations on it. What you can do, I'm not sure, haven't done a research on it, but they claim to have a quantum computer with some practical applications you can use. Magic Q Technologies is another company out in East Coast US. They claim to have a quantum cryptographic channel created, and you can have Alice and Bob and send information back and forth. So you can Google that too. So regarding devices in the field of quantum computing, what are we looking at? What kind of possibilities are existing in this world, right? So we are in the world of quantum communication or quantum cryptography, which is still known. We're talking about BB84, sending information back and forth, not breaking the protocol. Those things are well understood. In the world, when you go past, think about quantum sensors, widgets, photocells, quantum games and toys. I don't know. The world is open, right? You have these resources provided to you by this physical theory. Now it's up to you to find ways and means or innovation to look at what you can do. Even the fact theoretically that you can solve certain computational problems in computer science using this is fascinating. ENIAC, 1946. Everybody probably have seen this picture before, right? The father of computers, for example. Such a big machine. What we have today is all a same example in a phone, right? This is the von Neumann architecture, basically. You just have an output, an input, and a processor running in the background with a memory. That's exactly what this machine was doing. We have come within, 50, 60 years at the most from that to this. Imagine, this is a quantum computing lab currently. Within the next 30 to 40 years, what could have happened? We all know, we are in IT, how fast this world is going, right? From 2000, when I didn't even have an iPhone, I didn't know what an iPhone is, to today I can't live without this, right? It's been like 18 years. And now you would have something which you can use. Example from IBM, the 7-qubit quantum computer I was talking about. 15 changed into 5 and 3. The fact that you can refactor back a prime number into prime factors, as I said, there are possibilities to break RSA algorithm or those kind of cryptographic protocols because they're based on the mathematical difficulty of something happening. Ion trap quantum computing. They're working on at Simon Fraser University out in West Coast on using ions to do quantum computing. This is the D-Wave system. So they have, that one was an old picture. This is a new one. They have this in their lab. So this is a reality. I just want to show you that this is not, this is not theory anymore. There are some practical implications of it. And the fact that we will be moving towards it, there is no other way unless you want to have more faster computers. You got to have transistors. You got to have systems much faster. You are ultimately moving towards the speed of light. You're ultimately moving towards that miniaturization of devices that these things will come into reality, one way or the other, right? Google has a quantum error correction chip. You got, I don't know how many chips are, how many qubits are. There are 9 qubits. You actually have those 9 qubits. They created this chip. These 9 qubits talk to each other, and they correct each other's errors. So if I'm a 1, even though qubit is not a 1 at one time, it's 0 and 1, the other party is a 0, and it's supposed to be a 1, I will do coherence with it. That's because you're closer to it. You can influence its state, and I will correct it back to its normal state, which is the correct one. Think about it. You're correcting errors using qubits. Now, this is stored. You can do it in a communication channel, too. Quantum random number generator. This could be a reality. I guess it's a reality. I'm not sure how true this picture is. I took it from Google. But, just like there's no real random number generator in a computer science, like a normal computer, as we all know, right? This is classical physics. There's no full 100% randomness out there. You are using some clock cycles. You're using something of the electrical signals to try to create random number generators. But in the world of quantum mechanics, as we all see, the Schrodinger's paradox and the fact that you will always have randomness until you measure it, you actually could have a real random number generator application through a quantum computing device. Atomic clocks, another big one, right? You can actually have clocks, as we all know. These clocks, again, have some error existing because these are classical clocks. And so the moment you go into the world of atoms, the precision increases. The moment the precision increases, you can actually have clocks which are very, very correct. I don't know if they can ever be 100% or fundamentally correct, but you can increase that precision to a point. So that's another application. Stability equivalent to losing less than 1 second in 300 years. That's the end of my presentation. I like this Winston Churchill as a quote. It keeps me reminded, right? Now, this is not the end. It is not even the beginning of the end, but it is perhaps the end of the beginning. We have just ended a concept moving into an uncharted territory where the possibility is open. So thank you very much for your time and attention. I hope it was good.